Hi, I'm Dale Bland, Principal and CEO at Marshall Institute. First, let me thank you for having attended our seminar, Maximizing Asset Reliability Through Preventive Maintenance. This seminar represents a coming together, if you will, of the best of two other great Marshall Institute seminars, PPM, Preventive Predictive Maintenance, and PMO, Plant Maintenance Optimization. This e-learning lab is intended to complement the seminar you attended by reviewing key concepts and learning points covered in the class, and providing you with the opportunity to refresh your memory and perhaps share those concepts and learning points with your colleagues and coworkers, and in that way assisting you in your journey to maintenance excellence. Let's begin with some basic definitions. First of all, let's make sure we have a good working definition of preventive maintenance, usually abbreviated PM. Preventive maintenance can simply be defined as any activity that does any or all of these things: reduces the number of equipment failures, reduces the magnitude of equipment repairs or repair cost, reduces the product loss or production downtime associated with equipment failure or repair, or reduces deterioration in the productive capacity of the equipment over time. Generally speaking, preventive maintenance can be done on the basis of time or condition. If it's done on the basis of time or cycles of operation without regard to condition, it's called interval-based maintenance. That's on the right side of the chart. If it's done on the basis of condition, however, that is, whether anything is done or not depends on some found condition, it's called condition-based maintenance. That's on the left side of the chart. As far as this program is concerned, the term PM, or preventive maintenance, refers to both of these types of maintenance, both interval or condition-based. If you hear me refer to PM, I mean to include both of these types of maintenance in that term. Sometimes condition-based maintenance is called predictive maintenance, or PDM. But if so, it too simply refers to doing maintenance on the basis of some measured or observed condition. Having said that, sometimes PDM is used to refer technically or specifically to high technology tools and instrumentation such as vibration analyzers, ultrasonic or infrared detectors, eddy current measurement, oil analysis, and so on. However, for the purpose of this program, condition-based maintenance simply means maintenance on the basis of condition or measurement. Generally speaking, corrective maintenance, abbreviated CM, is any maintenance activity which is required to correct a failure that has occurred or is in the process of occurring and is aimed at restoring an asset to a condition in which it can perform its intended function. Corrective maintenance, CM, can be immediate or deferred. It can be unplanned or planned. The term corrective maintenance is usually synonymous with the term corrective work. CM from PM is a category of work that results from preventive maintenance activity, either interval or condition-based. That is, work that is identified in the course of doing either of those activities. It is work that has been identified as required, but not necessarily immediately, so that such work can be put into the system on a work request to be properly channeled through the work order system with the right priority, sufficient planning, assignment to the right resources, and scheduling in time so as to achieve the work in the most efficient way possible, at the lowest cost possible. It rarely should be performed at the time of PM unless to ignore it could produce adverse consequences or unless it is truly minimal or trivial in terms of time and or materials. When PM is working, PM is one of the three legs on the planning and scheduling stool, along with stores management and work management. When all three are working together, the majority of maintenance work can be done with minimum delay in cost at maximum effectiveness. It's been proven time and time again. Planning and scheduling is one of the most effective ways to control cost and improve maintenance productivity. Good PM practice is an enabler to good planning and scheduling. If you do preventive maintenance right, there's a business case to be made. Let's talk about that. Think about what happens if you don't do preventive maintenance right. What happens? Poor utilization of capital assets. There's high capital replacement cost. We have excessive maintenance and operational cost. We have poor reliability, high failure, unplanned downtime, lost revenue, safety and environmental risks are high, and so on and so forth. These things can be fatal, especially if you're in a competitive marketplace. And who isn't these days? The benefits are clear. Here are some of the things by which you can make the business case. You have at least three ways to make your case. PM can reduce cost, that is, cost going into the product, increased revenues, that is, increase the product going out the door, or minimize capital expenditures, such as minimizing the capital that it takes to make all that happen. Let I'm showing you an actual example of what optimizing your PMs can do for you. Here's what resulted from a 3-day PMO workshop at a medical device manufacturing company in Florida on a line that produces safety needles for hypodermic syringes. The line could sell as many needles as it could produce. There were 2 of these lines, and the savings shown does not include application to the second line. This is one line only. Optimizing the PM program on this line resulted in eliminating non-value-added tasks, moving some PMs from offline, where the line had to be down, to online, where the line could be kept running, and extending the interval on more than half the task without harm. The old PM strategy required 8 hours downtime every 4 weeks. With the changes, the new strategy now calls for only 6 hours of downtime every 4 weeks. The downtime lost production savings alone is almost $200,000, and when combined with the 250 hours of labor savings due to fewer PMs, total savings now push close to $300,000. Not bad for 3 days of work. Maximizing asset reliability depends on the application of the concepts of reliability-centered maintenance, so it's important that we understand the basic principles of RCM. Prior to the development of the RCM methodology, it was widely believed that everything had a right time for some form of preventive maintenance, usually replacement or overhaul. A widespread belief among many maintenance people was that by replacing parts of a product or overhauling it, that the frequency of failures during operation could be reduced. Despite this previously commonly held view, the results seem to tell a different story. In far too many instances, PM seemed to have no beneficial effects. Indeed, in many cases, PM actually made things worse by providing more opportunity for maintenance-induced failures. RCM comes out of research in the 60s, which showed that not all failures were age-related or service-related, and because of that, overhauls, which were thought to ensure reliability, did nothing of the kind. PM often seemed to have no effect at all, and overhauls had no effect on reliability, and in fact, were found to actually decrease reliability. Let me show you what that means. In the 60s, the DCA had over 400 overhaul components. At that time, U.S. commercial airlines were having around 60 crashes per million takeoffs. Most of those crashes were caused or related to equipment failure. Today, modern aircraft, this is true of the DC-10 for example, may have as few as 7 overhaul components, that is, replacement based on fixed intervals of calendar time or service hours. What's remarkable is that strategies based on RCM have reduced crashes per million takeoffs to less than 2 crashes per takeoff by the late 70s and early 80s, and it's getting better. That number was 1.4 in 1989. It was 0.2 in 2008. 2010 was a year in which there were no deaths in the U.S. airline industry at all, 0. Only 3 in the 5 years before that. Flying on a commercial aircraft is one of the safest forms of transportation there is. It is simply mind-bogglingly safe to get on a commercial flight and go somewhere. That's because of RCM, the right maintenance being done the right way by the right people. The RCM breakthrough was the realization that maintenance is not about preventing failure, it's about preventing the consequence of failure. Some kinds of failure can't be prevented. Even normal wear and tear leads to failure. You can't prevent that. What you can do, though, is to make sure that it doesn't bite you in the butt, so to speak. That is, do something before the failure results in loss. RCM is a structured process that identifies every possible or probable failure mode, and through a structured series of questions and a way of thinking, decide how best to deal with those failures, both technically and economically. The RCM method uses the answers to 7 very basic questions to help determine the best maintenance task to implement for highest reliability at lowest feasible cost. The RCM method uses the answers to 7 very basic questions to help determine the best maintenance task to implement for highest reliability at lowest feasible cost. RCM can be a time-consuming, resource-intensive process. There are ways to reduce the amount of time and resources required to apply RCM principles, however. PMO optimization is one of those, and we'll be talking about that later. The key, however, is understanding the basic principles of RCM and the 7 basic questions that need to be asked about each failure mode. Just remember, it's the primary goal of reliability-centered maintenance to ensure that the right maintenance activity is performed at the right time, at the right frequency, with the right people, and that the equipment is operated in a way that maximizes its reliability without harm to people or environment, and with only minimal operational or profit loss. This is achieved by addressing the basic causes of system failures and ensuring that there are organizational activities designed to prevent them, predict them, or mitigate them based on the actual operational context in which they are occurring. The good news is that failure is a process, not an event. What this means is that most failures, perhaps all failures, are associated with some form of deterioration or physical drift, which takes a finite amount of time to actually reach functional failure. That is, when the something no longer performs the function for which it was designed or installed to do. Think about a bearing or drive belt. Wear is a kind of failure that occurs over a long period of time, essentially from the very beginning, but functional failure of the bearing, that is, when the bearing no longer facilitates rotation of the shaft it's on, doesn't occur for a long time. That can be months, maybe even years, over millions of cycles. Many times this deterioration, this physical drift, whatever it is progressively visible or measurable evidence that something is changing, which if left alone will inevitably lead to functional failure. Thus what we have is called the P to F curve. Let's talk about the P to F curve. The P to F curve gives us a chance to see deterioration, that is failure, in progress. If the interval between P, the time we can detect the deterioration or physical drift of the heat or sound, vibration, contamination, etc., and F, the time at which function is lost, is long enough, then we may be able to avoid F altogether. We call the time between P and F the P to F interval. If the P to F interval is days, months, or years, we have a good chance of seeing failure coming before it gets here, and do something about it, and at the very least avoid the consequence of it. The process cannot be prevented, but the consequence of the failure itself most certainly can be. On the other hand, if the P to F interval is measured in milliseconds, or even seconds, we may not be able to take advantage of it. If the P to F interval is milliseconds or less, it may be considered sudden or instantaneous for all intents and purposes. Failures with short P to F intervals are hard to deal with. Sometimes the P to F interval may be very detectable, sometimes through our own senses using look, listen, and feel. Here's an example of a bearing failure. We've all seen this sort of progression, no doubt. Even here, the P to F interval may be long enough to avoid any surprises. That is, even our own senses may be able to give us enough early warning of impending functional failure of the bearing so as to avoid total failure, that is, seizure, when we could least afford it. So here's the ideal situation. Deterioration or physical drift is occurring over time, at a rate sufficiently slow as to allow us to take action to do whatever is required to avoid failure or its consequences in plenty of time. From the time we detect the failure in progress, we have plenty of time to prioritize, plan, schedule, and execute the work, avoiding F entirely. In addition to the P to F interval, there's a concept called safe interval. Let's talk about that a little. There are failures for which time in service is a very good predictor of failure. If that's the case, that is, if a failure is very predictable, based on time in service or cycles of operation, we may want to simply use an interval-based replacement or refurbishment strategy. It avoids frequent inspection or detection, and simple replacement on a regular basis may be both safe and economical. Of course, the interval you pick depends on how much risk you're willing to assume. The curve is never perfect. If you wait too late, you may be running some increased risk of failure. If you replace too soon, you lose useful life and spend money unnecessarily. We call this the safe life. You pick it based on experience and risk tolerance for the consequences of being wrong. The smaller the consequence, the more risk you're willing to take. The larger the consequence, the less risk you're willing to take. The more you will reduce the interval until you feel sufficiently safe. Timing chains on auto engines may be a really good example of this type of failure characteristic. The Toyota Camry required the timing chain to be replaced at 90,000 miles, not more. I was told that it might go further than that, but anything beyond that was taking a pretty big risk. If the chain actually failed, it would cause catastrophic damage to the engine. The chain replacement, though not cheap, was far preferable than the consequential repair if it failed. When you think about it, maintenance has only about 3 basic options. It's our job to pick the right one. For example, if you don't know when it's coming, but you can see it coming when it does, then start looking, and then do something only when it's required, that is, before something bad happens. That's condition-based monitoring, CBM or PDM. If you know when it's going to happen, then you don't have to do anything until it's time, that is, before it happens. That's interval-based PM, change-out, or overhaul. If you can't see it coming and you don't know when it's going to happen, there's not a whole lot you can do. It will happen. If you still don't like the consequences, then there's a few things you can consider at this point, but they're not exactly maintenance strategies. Things like modify, redesign, or redundancy, or perhaps some other things you could do to reduce consequence. Or if it doesn't cost much or hurt much, even when it happens, then it may not be worth doing anything. These last two are basically no maintenance required, run to failure, no scheduled maintenance. And then, of course, you still may be able to reduce the consequences. A common feature and tool of RCM-based analysis is to provide a kind of decision tree to logically and consistently select the proper maintenance strategy for virtually any circumstance or context, based primarily on the consequence of loss, but fundamentally screens alternative strategies based on technical feasibility and economics. This logic tree is a useful example, but it's only one of perhaps hundreds of such logic diagrams available in the literature. Here's a powerful tool that Marshall Institute finds very useful for arriving at the appropriate strategy for any given failure mode. It has the virtue of very rapidly telling you what strategy is even possible given the nature of the failure itself. This chart is based on the fact that maintenance strategy can be determined for any given failure mode based on only two basic criteria, that is, whether it's a function of age or not, and how fast it progresses once it has started. Number one, is the failure a function of age, or can its onset be considered random? That's the vertical axis on this chart. Age-related, predictable, or random, unpredictable. Secondly, once failure starts, how fast does it progress? In other words, what is the rate of deterioration? Does it progress gradually, that is, does it have a useful P to F interval, one that is sufficiently long to be practical, or does it fail suddenly, that is, the P to F interval is non-existent, or so short as to be essentially non-existent? That's the horizontal axis on this chart. Sudden, that is, the P to F is not usable, or gradual, there's a usable P. So there you are. Depending on which quadrant you arrive at, will determine the strategy or strategies that you can use for the particular failure mode being analyzed. For example, if you get to the upper right quadrant, that is, your failure mode is both age-related and gradual, you've got the best of all worlds. It's predictable, and it has a usable P to F. You can choose interval-based maintenance or condition-based maintenance based on what's most economical or practical. A prime example might be drive belts, properly applied and properly installed, or maybe automobile tires. If you get to the bottom left quadrant, that's where your failure mode is both random and sudden. There's almost nothing you can do. You don't know when it's going to happen, and when it does, it's over. You're going to have those failures. The only thing you can do, as we said before, is to reduce the consequences. The prime example here might be the rock through the windshield. The other two quadrants should be more or less self-explanatory. Upper left quadrant, age-related but sudden. Being age-related, it's predictable. Even if it's sudden, it's tied to an age in such a predictable way that you simply may be able to resort to a replacement on a safe life basis. Prime example of that might be the automobile timing chain, or maybe the spark plugs. The lower right quadrant, random, gradual. You don't really know when it's going to start, that is, it's random, but when it does, it takes time, gradual, to go from P to F. That means the failure or its consequence can be avoided by inspecting or measuring often enough so as to never miss the P to F interval. That is condition-based maintenance. Interval-based maintenance simply won't work. The prime example here might be the propagation of a crack in sheet. The failure quadrant is a great tool. We use it a lot in PM optimization. And PM optimization is the next thing we're going to talk about. PM optimization is a process which uses the principle of RCM to improve an existing maintenance program and eliminate defects. It starts with the existing maintenance program for the assets in use and the existing failure history, whether it's formal or informal. PM optimization is a process to increase both the effectiveness and the efficiency of the reliability strategy. It increases the effectiveness of the strategy by optimizing the current preventive or predictive procedures, by making sure that the right procedures are being done by the right people at the right frequency, and addressing failures that are not addressed by the current maintenance and reliability strategy, and managing and reducing the consequence associated with the failures that we're having, and selecting effective alternative strategies when it's appropriate. PM optimization increases the efficiency of the reliability strategy by 1. Making sure that the consequences of or the losses associated with certain failures warrant the cost of doing something versus nothing. Secondly, eliminating strategies and procedures that add little or no value. Thirdly, writing tasks and procedures clearly, applicable to the equipment to which they're being applied. Fourth, assigning tasks and procedures to the right resources. Fifth, writing tasks and procedures so that they can be accomplished efficiently without waste of time, money, or effort, and so on. PM optimization is successful by removing all the maintenance tasks that serve no purposes or add no value. By eliminating duplication of effort where different people or different crafts are performing the same PM to the same equipment. It's not unusual, for example, to find maintenance people doing a task weekly that operators are doing daily. If that's the case, one of those PMs is unnecessary. By moving to a mostly condition-based rather than time-based PM, that is, doing maintenance only when it's necessary rather than time or interval whether it needs it or not. Adding maintenance tasks to take care of failures that we're having. And lastly, spreading the work. The heart of the PMO process is a workshop that provides input from the people who know the equipment best, the operators and maintainers of the equipment under review, along with a facilitator. Remember, it's a structured process. It starts with existing PMs and current failure history, from which dominant and probable failure modes are derived. Those failure modes are analyzed using RCM logic to create improved maintenance strategies and converted into new or improved PM procedures, reinserted into your current PM program. Let's look at the PM optimization workshop process, before the workshop, during the workshop, and after the workshop. Before the workshop, we're going to select the assets in which we want to improve reliability. We're going to gather current information and data, such as current PM tasks, the current failure history, the spare parts usage, the current operator tasks and procedures. We're going to get some labor rate and downtime information too. We're going to make a list of all the known or probable failure modes that have to be dealt with during the workshop. During the workshop, we're going to gather the input from operators, maintenance, and other people who may be participating. We're going to evaluate the consequences of each and every one of the listed failure modes. We're going to analyze the failure modes according to the RCM and PMO logic tree or the failure quadrant diagram in such a way that we can determine the maintenance tasks that are both technically feasible and cost-effective to do. After the workshop, we're going to finalize things by grouping all the maintenance tasks that we've arrived at by frequency and craft. We're going to create the maintenance procedures out of that. We're going to review and approve those maintenance procedures. We're going to put those into the CMMS. We're going to communicate those new procedures to the appropriate people. We're going to implement and execute the procedures, and then we're going to audit and approve them as required to make them what we need to be. Having now selected the appropriate maintenance strategies based on failure and consequence, we now have to select appropriate maintenance strategies based on technical considerations and economics. Section 5 presents a rather comprehensive overview of the practical considerations of major maintenance tools and techniques that are available to you. Remember, we only have a limited number of choices, primarily 3. Interval-based, that is, when there's predictable, safe life associated with the failure. Condition-based, when there is a usable, practical PDF interval associated with the failure. Or run-to-failure, when the cost or consequence of failure is negligible, or the cost of doing nothing is less than the cost of doing anything. And depending on consequence, we may have 2 further alternatives. If the failure simply can't be avoided, we may simply run to failure, but use a redundancy strategy to avoid the consequence. Or if the failure is really a big problem, that is a major consequence, especially loss of life, we may need to modify or redesign it to avoid it entirely. Section 5 dedicates a significant amount of time and attention to the importance of operator involvement in maintenance, typically through specific sorts of activities which we at Marshall Institute call CLARE: cleaning, lubrication, adjustment, inspection, and repair. Operators are our first and best line of defense. We should be doing everything we can to engage the hearts and minds of our operators in basic equipment care. They are truly the eyes, ears, and noses of the maintenance function. So remember CLARE. Cleaning. Dirt and contamination are the enemy of maintenance. It's been shown that operators, just by keeping equipment clean, can detect 75% of impending failures. Lubrication. Lubrication is the foundation of preventive maintenance, and it can often be done as an operator task. Properly trained operators can perform many, if not most, of the lubrication duties on their machines, freeing maintenance to do more complex, value-added activities. Adjustment. Regular adjustment and tightening is an operator duty, and thus avoids entirely what is a chronic problem in most plants, loose and missing fasteners. Inspection. Early detection is the secret to preventing failure. Who best should be looking for early signs of deterioration than an experienced and well-trained operator? Remember, they can see 75% of this stuff coming sometimes. Repair. Operators can be trained to perform minor repairs and replacements, filter changes, belt changes, valve seat changes. These things are often more complicated than replacing the wiper blades on your car. Again, freeing maintenance to do more complex, value-adding activities. It could be said that the foundation of a good preventive program is lubrication. After all, virtually every machine needs lubrication. Lubrication performs a myriad of tasks, things like friction control and wear control for moving parts, corrosion protection. Contaminants are often removed by the lubricant bed or filtration systems itself. Temperature control. A lot of machines depend on the cooling nature of the lubricants themselves moving through the system, especially oil. And contamination control. Contaminants are often removed by the lubrication systems. Most of the technologies discussed permit the user to extend the range of human senses so as to provide the longest P to F interval possible, thus allowing the maximum amount of time to take action to avoid failure or its consequence. Here are some of the most common condition monitoring tools and techniques discussed in greater detail in the seminar and the book provided with the seminar. Run to failure and redundancy can be powerful maintenance strategies in their own right and can often be the most cost-effective strategies available depending on the circumstances. The run to failure strategy is the one that says don't fix it, don't prevent it, let it fail. This works if the consequence is negligible. It may very well be more cost-effective to do nothing than to do anything at all. Even then, the consequence can be reversed further by redundancy, perhaps even eliminated entirely. Generally, the decision to use RTF, run to failure, or redundancy is a question of economics. The RCM PMO logic tree illustrates perfectly how you get to a run to failure or redundancy strategy. If the failure doesn't matter, that is, the losses are negligible, path A, the run to failure mode is obvious. Let it fail. Take the risk. If the failure does matter, path B, but neither PDM, that is seeing it coming, or PM, doing something on an interval-based frequency, are possible or economical, then redundancy is worth considering. If it's economical, do it. If it's not economical, it's simply back to run to failure. There are no other choices. At the seminar, we talked a lot about how to write complete, clear, unambiguous PM procedures to make sure that they're both efficient and effective. Let's review some important points to remember. Every PM procedure should contain 5 crucial elements. What is to be done, how it is to be done, what is acceptable, what's not acceptable. For example, in condition-based, what criteria or specification determines pass or fail. On interval-based, what criteria or equipment function must be ensured after task completion to make sure that things are going to make it until you get back. Number 4, what course of action should be taken if the findings are unacceptable? And 5, what do we do to ensure safety? Now, let's make a note. Safety is not last, it comes first, but when writing a PM, we usually need to know the what and how before we can really get a good handle on what safety precautions should be noted on the procedure. So safety is first, but it's first and last. First, make sure you don't forget to consider it. And last, make sure you didn't forget to include it. Remember the 3 primary elements of a task statement. Most tasks, that is condition-based tasks usually, should contain the instruction, the acceptable limits, if any, and what to do if an unacceptable condition is found. The only exception may be that interval-based tasks need contain only the instruction. By definition, acceptable limits are not needed because an interval-based task is not looking at condition. An interval-based task is being performed without regard to condition. It's going to be done whether it's needed or not. We ended the seminar with some advice on developing and implementing an effective PM program. It's a kind of 12-step program, no pun intended, but it may rid you of your addiction to reactive maintenance. So here's 12 workable steps. Number 1, rank your physical assets by criticality, that is, by the degree to which failure may risk people, environment, production, or cost, in that order. Step 2, select equipment that matters for initial analysis. Forget the trivial stuff. Step 3, get your equipment data together, specifications, prints, schematics, manuals, OEM catalogs, and such. Step 4, gather current PM and failure history. Use formal CMMS records if possible. If you can't do that, get some mechanics and operators familiar with the equipment and pick their brains. They'll remember 80% of whatever happened to their machine probably. Step 5, define the failure modes associated with the PMs and the failure events. Use the failure quadrant and the RCM logic tree to determine the strategy that works for every failure mode. Step 6, write the PM task using the key 5 elements that we showed you. Step 7, group the task frequency and craft, including operator tasks. Create PM procedures from the group tasks. Step 8, get the necessary approvals for the procedures and document formal maintenance plans for each piece of equipment or line. Step 9, format and enter the approved procedures into your CMMS system. Step 10, develop and document your formal PM policy. Assign priorities, clarify responsibilities, and define the metrics and KPIs that you're going to use. Communicate the policy plant-wide to everybody that needs to know it. Step 11, schedule and execute the PM program. There'll be some things you didn't get right, so revise and improve them as necessary. Step 12, sustain the PM program through auditing, rewards, and recognition, and the disciplined use of good metrics and KPIs. This metrics and KPIs things cannot be overemphasized. If you're going to improve something, you're going to measure something. Consider the metrics and KPIs on this list as your starting point. You'll probably think of others as you go. Remember, select your measures, publish your measures, that is, display and communicate your measures, and 3, improve your measures.
Well, that's it for the Maximizing Asset Reliability e-learning lab. Thank you for attending the seminar. If you have questions about any of this material or about maintenance and reliability in general, you may call us at any time. If you get a chance, visit us at our website. You'll find all sorts of articles, blogs, and videos designed to help you and your organization move along the journey to maintenance and reliability excellence. We hope to see you and others in your organization at one or another of the 50-plus seminars that we conduct every year. Thanks again. Goodbye.